Hey everybody, welcome back to chemistry. And in this presentation, what I want to do is talk about what electrolytes are. So electrolytes are compounds that when you dissolve them in water, allow the water to be conductive. In other words, the water can conduct electricity. So I'm going to talk about what makes some compounds allow the water to be conductive in a minute. But the first thing I sort of need to talk about is how do you test whether water is conductive or not? And so you need a particular apparatus to do this, which I have there in that drawing in the lower left of the slide. So let's look to the far left of that picture there. And so in the far left, what you can see is I have a beaker of water, and that water is pure water. You can think of it as distilled water. So pure distilled water will have absolutely nothing in it other than water molecules. So it has no ions, it has no other molecules, it's just pure water molecules. So to test its conductivity, what you can do is you can drop two electrodes into the water, and then those two electrodes will be connected to the house voltage. And then on that line to one of the electrodes, you have some kind of device that indicates that current is going through those wires to those electrodes. And so that device might be a light bulb. Now, what happens is when you plug in those two electrodes, one of the electrodes will develop an excess of charge that will be negative, and then the other electrode will develop an excess of charge that will be positive. And then what that does is it creates a voltage between the two electrodes. Now, the water cannot conduct electricity between those two electrodes, and if that's the case, then you do not have a complete circuit going through those wires. You have no electrons or electricity flowing through those wires, despite the fact that you have a voltage in the electrodes. If that is the case, then the light bulb is not turned on. Now, look at the center beaker there. So there we have pure water again, but this time we've added sodium chloride into the water. And so these positive and negative ions, when added to the water, make the water conductive. And so when the water is conductive, that means electricity can pass through the water. That completes the circuit between the electrodes, and then electricity flows through the lamp, it turns it on. Now, the last example of the beaker there, we have water again, but instead of having ions from sodium chloride into the water, now what we have is a different molecule added to the water. The different molecule is sugar. Now, sugar will dissolve into the water, but sugar will not allow the water to be conductive. And so after you add sugar to the water and you plug that in, you will get no conduction of electricity through that sugar water, and so the light bulb will not turn on. Just to point out again, anytime you have a compound that dissolves in the water and allows the water to conduct electricity, it will be an electrolyte. So in this case, the sodium chloride added to the water that allow the water to be conductive, that is an electrolyte. Here, the sugar, when it added to the water, it did not allow the water to be conductive, so it is not an electrolyte. So let's figure out what is it about the sodium chloride that allow the water to be conductive, but what is missing from the sugar so that the sugar did not allow the water to be conductive. Okay, so what you need in an electrolyte to allow the water to be conductive is that electrolyte needs to be a soluble compound that dissociates into ions. And so, for example, when we added sodium chloride into the water, the sodium chloride solid dissociates into individual sodium ions and chloride ions. And so each sodium ion has a positive charge and each chloride ion has a negative charge. Now, we could have used another soluble ionic compound like potassium chloride. When potassium chloride dissolves into water, it will dissociate, creating ions. There will be potassium ions, which are positive, and chloride ions, which are negative. And there on the right, I've sort of described in a picture this process. And so what you can sort of see is that the water molecules that are surrounding the sodium chloride crystal are sort of ganging up on the individual ions and pulling them off in the water. And so you're freeing and releasing into the water the purple potassium ions and the green chloride ions. And so what you have now is you have free ions in the water. It is the presence of free moving ions in the water that makes the water conductive. So in order to have an electrolyte, it must be a substance that dissolves in the water and releases ions that are free in the water to move around. That'll make the water conductive. Now, why wasn't the sugar an electrolyte? Why did the sugar not allow the water to be conductive? Well, the reason is you can dissolve plenty of sugar in the water, and so the sugar molecules will dissociate from one another. You'll have separated sugar molecules out in the water. Now, the sugar molecules are kind of big, just to note. Each sugar molecule has 12 carbons, 22 hydrogens, and 11 oxygens. So each individual sugar molecule is pretty big. However, in that molecule of sugar, there are no ions in it. So one of the requirements to make water conductive is that the substance has ions, and sugar has no ions in it. So despite the fact that it dissolves very well in water, it does not create ions, and so it cannot make the water conductive. Okay, so you need to know what kinds of compounds are strong electrolytes and what kinds of compounds are not electrolytes. So let's go through the strong electrolytes first. And so essentially, if you have any kind of soluble ionic compound, that is a strong electrolyte. And the reason is because when that ionic compound dissolves in water, if it's soluble, it will completely dissolve, meaning that the crystals will completely dissociate, releasing oppositely charged ions in the water, and that will make the water conductive. Now, there are classes of molecules that are not electrolytes, and so you already know that sugar is not an electrolyte, but can we sort of generalize further? And the answer is yes. Ionic compounds, because they dissociate to produce free ions in water, are great electrolytes. On the other hand, molecular compounds, even though many can dissolve in water, are not electrolytes because they do not produce ions. And so sugar is an example of that. It's a molecular compound that dissolves perfectly well in water but does not create ions. And then there are other molecular compounds as well that would not be electrolytes. So for example, ethanol is a molecular compound. So it dissolves extremely well in water, but what it does not create ions, and so it would not be electrolyte. And so there are other things like gases, like oxygen and carbon dioxide and hydrogen gas. They can dissolve to some degree in water, but when they do, they are not in the forms of ions, and so they would not allow the water to be conductive. So those molecules as well would not be electrolytes. So just to summarize, soluble ionic compounds are going to be strong electrolytes, while molecular compounds will not be electrolytes. Now, we need to talk a little bit about the difference between strong electrolytes and then weak electrolytes. And so let's talk about the kinds of classes of molecules that would be strong electrolytes. And so one class of molecules are the ones I just mentioned, which are soluble ionic compounds. So I have some examples there. The ones you already know about, like sodium chloride and potassium chloride, they dissolve perfectly well in water and produce ions, but there are other ones you learned about earlier, like barium hydroxide or potassium nitrate, things like that. Now, strong acids are also strong electrolytes. And the reason is, if you have a strong acid like hydrochloric acid, when you dissolve hydrochloric acid in water, all molecules dissociate into hydrogen ions and chloride ions. And so all molecules of HCl create all these ions that are mobile to allow the water to become conductive. So whenever you have a strong acid which is dissolved in the water, so for example, HCl is one, H2SO4, which is sulfuric acid, HNO3, which is nitric acid, all strong acids are considered strong electrolytes, again, because they're producing a lot of ions which are mobile in the water. Now, how about the class of molecules that would be weak electrolytes? And so what you might imagine here is that if you have ionic compounds, but they're not very soluble, maybe they're only sparingly soluble, meaning only very small bits of the ionic compound can dissolve in the water and release a few ions into the water. They are releasing some ions into the water to allow the water to be conductive, but it's not very conductive. And so a weak electrolyte would be an ionic compound that is not very soluble. And so there's some examples of those. And so for example, silver sulfate is an ionic compound. It's comprised of silver cations and sulfate anions. But when you add silver sulfate in the water, very little of it dissolves in the water. And so it produces very few silver and sulfate ions in the water. And so a few ions are there to allow the water to be a little bit conductive, but it's not going to be very strongly conductive. Another good example would be calcium hydroxide. You can dissolve a little calcium hydroxide in the water, producing a few ions, which will allow the water to be a little bit conductive. Now, another class of compounds that are also weak electrolytes are weak acids. So for example, the classic example of a weak acid would be acetic acid. And so acetic acid, its formula is HC2H3O2. Let's say you add a lot of acetic acid molecules into the water. What will happen? Well, of all those acetic acid molecules, only a few will dissociate, meaning only a few of those molecules will release hydrogen ions and acetate ions. The rest will be still HC2H3O2. So you only get a few ions produced for all the molecules of acetic acid you have. And so that is enough to make the water a little bit conductive. Okay, so now what I want to do is talk about how is it that ions in water allow the water to be conductive. And so I want to talk a little bit in some detail of this electrode system that sort of measures whether the water is conductive or not. So I want to add something to the system here. So we have an electrode on the left, which is positively charged, and it goes into the wire, which it goes into a battery. And then you have a wire leaving the battery on the right and going to the electrode on the right. So into this system, let me add a symbol for a light bulb. And so here, this curly cube symbol here is just the symbol for a light bulb. So here's my light bulb here. So we have a light bulb here that's in the wire. Now, let's say, just pretend for a moment there are no ions there. It's just pure water. So what does the battery do? Well, you can think of the battery as an electron pump. What it'll do is it'll pump electrons toward the negative electrode like this. So electrons are heading toward the negative electrode, and they come out of the positive electrode like this. So the battery gets the electrodes with either an excess of electron charge, so it's going to be negative charge on the right side, and a deficiency of charge because there's deficient electrons on the left side, and so that will be positively charged. Now, right now, again, pretend there are just no ions in the water here. Right now, there is going to be no circulation of electrons in the system once you have loaded your electrode on the right with electrons and you have removed electrons from the electrode on the left. You're going to get no circulation of electrons through this system. And so the only way you can get movement, circulation of electrons through this system to turn on this light bulb here is to add something to the water to allow the water to be conductive so it can complete the circuit. So ions do that. So let me explain how that works. And so again, once you add ions, you're going to add negative and positive ions to the water. The negative ions are going to be heading to the positive electrode, and the positive ions are going to be heading to the negative electrode. So let's think about what's going to happen when the negative ions meet up with the positive electrode. So we originally had a deficiency of electrons in that electrode. And so before we added the ions, the current was not moving through the wires. But as soon as you throw the ions in, the negative ions move to the positive electrode, and they will have each one extra electron, and they will deposit that electron in the positive electrode. And then once that's done, then basically what's going on is that these negative ions are replenishing this electrode with electrons. Then the electrons can be sent through the wires and they'll turn on the light bulb. Now, at the same time that you're replenishing electrons into this electrode by negative ions, on the other electrode, you have to have ions that take away the excess electrons that are building up. And so those ions that do it are the positively charged ions. And so the positively charged ions will meet up with this negative electrode, and they will collect the electrons that are going into this negative electrode. And then when they do that, they're no longer positive. They become neutral atoms. And so as long as ions are there, the negative ions will replenish electrons into the positive electrodes so that those electrons can flow through the wires. And then once the electrons get to the negative electrode, the positive ions will collect those electrons and then remove them. And so that allows circulation of the electricity through the wires, and that turns the light bulb on. So thank you for listening to that, and we will see you next time.